In chapter 9, we're going to get two new reaction types. We're going to learn about substitution reactions first, which was kind of hinted at the end of chapter 8 with the electrophilic aromatic substitution. And then in the back half of chapter 9, we're going to learn about elimination reactions. It's a pretty big chapter. We're going to have 7 videos altogether for chapter 9. And in this chapter is where we first start to explore group 2. Right? Remember there are those 4 families from your textbook. At the end of chapter 8, we finished off group 1. Here we begin group 2. Okay? What group 2 is all about is where you have something that's electronegative, right? A halogen, an oxygen, that's attached to an sp3 hybridized carbon. Right? That difference in electronegativity makes this bond polar, right? Putting a delta positive on your sp3 carbon. And that's what's kind of controlling the reactivity, at least here in chapter 9. And that's where we get these two new types of reactions from. If we have a substitution reaction, then we have a leaving group that gets replaced by something else, right? It substitutes for it. That's the top reaction here. That's what we're starting chapter 9 with. In an elimination reaction, the second half of the chapter, the leaving group gets kicked off, right? It gets eliminated from the molecule. So does one of the neighboring hydrogens, and it results in the formation of a double bond. Okay, so substitution, elimination, they kind of hint right there in the name. Something gets substituted for or something gets eliminated, but note the difference in the products. Right? Here we still have sp3 hybridized carbon. Here we got a pi bond. Okay? So at the end of the chapter, make sure you can predict which one of these will happen. So in chapter 9 and chapter 10, we're going to think about the different members of group 2, that family, starting with alkyl halides. And the reason we consider alkyl halides for pretty much all of chapter 9 is because they have really good leaving groups. Okay? And a leaving group is an atom or a group of atoms that's easily substituted or eliminated. And so in this case, we just have a single atom, fluoride, chloride, bromide, or iodide. Any one of those halogens that can be a good leaving group. Right? And this is useful, right? Alkyl halides are really common in organics because they have a propensity for these substitution and elimination reactions. And that permits you to quickly convert an alkyl halide to a different functional group. So let's see how we do that, looking at a substitution reaction first. And there are 2 types of each reaction, the substitutions and the eliminations. And so we're starting with what's called an SN2 reaction. Okay. And in this notation, S stands for substitution, and then it's a subscript capital N that stands for nucleophilic, and then 2 means it's bimolecular. Okay. Bimolecular means there's 2 molecules that are involved in the transition state in the rate determining step. Okay, so substitution, nucleophilic, bimolecular. The other type that we'll get later is SN1, substitution, nucleophilic, unimolecular. Okay. So SN2, let's see what that means. Okay. First, what is a substitution? Okay, because in chapters 1 through 8, we are looking at addition reactions. What's a substitution? Right. Well, here I have a nucleophile, right, because it's a nucleophilic substitution that is replacing the leaving group. Yep. So here, the hydroxide is a nucleophile. Okay. Bromine is the leaving group. Nucleophile replaces the leaving group, right? It substitutes for it. Kind of like the electrophilic aromatic substitution from chapter 8, right? It was substituted for it, but here we have a different mechanism. And these mechanisms are determined experimentally, right, through kinetic experimentation. And the rate law tells us that we have dependence on the concentration of the alkyl halide and the nucleophile. Okay. The second order rate law overall. And that means, like, if I double the concentration of the alkyl halide, I double the rate. If I triple the concentration of the nucleophile, I triple the rate. If I were to double both of these, it would quadruple the rate. So that tells me that both are involved in the rate determining step, which is a really valuable piece of information. That tells me the reaction is bimolecular overall. This slide is effectively just summarizing what I've already stated. Okay. And we also get some information from those experiments from the rate constant. Yep. The larger the value of the rate constant, the easier it is to do the reaction. Okay, so if you see a larger rate constant, K, that means it has a lower energy barrier. It's easier to get over that energy hump, easier to get to and achieve the transition state, and for the reaction to proceed overall. Okay. Now, another piece of information from kinetic experimentation, and we'll elaborate more on this in the second video, is their relative reactivities. Okay. As an alkyl group gets larger, okay, more and more substituted, the rate, more and more substituents rather, excuse me, the rate of substitution decreases. Okay, so something that's tertiary, right, with 3 alkyl groups on it, that really doesn't do substitution reactions at all. But as we go down to secondary, primary, or a methyl halide, right, those are the most reactive. Okay, so as the alkyl group gets more substituted, the rate of substitution decreases, right, as it increases in size, because it's all about sterics, as we'll see in just a second. Okay, or to put it opposite, as these alkyl groups are smaller, the rate of substitution increases for these SN2 reactions. Okay. And if you think about the reactions from chapter 7, where we deprotonated a terminal alkyne and then used it as a nucleophile to attack an alkyl halide, the examples in chapter 7 were always primary alkyl halides because they react fastest. Yes, unless you can use a methyl halide by just adding 1 carbon. Those were SN2 reactions in chapter 7. We just didn't have the notation yet. How about the stereochem? That gives me some information about what's going on. Okay. Now, for an SN2 reaction, we have what's known as inversion of configuration. If your electrophilic carbon, the one that's attached to the halogen, is part of an asymmetric center, if it was S, it becomes R, as we see on the slide here. If it was R, it becomes S. And either way, it flips. It's an inversion of configuration if you have an asymmetric center. So that's the last piece of information from experiments. Okay, alkyl halide and nucleophile are involved in the transition state. Solid piece of information there. Relative rate, right? Primary faster than secondary, faster than tertiary, and as we just saw, inversion of configuration. Okay. These are important to identify in your reactants, and it gives us the information necessary to draw the mechanism. And this is as simple as it is. Your nucleophile comes in, right? Lone pair of electrons comes in, attacks your electrophilic carbon with that delta positive. At the same time, this bond breaks going to the halogen or the electronegative group when we get later, leaving groups later on, right? Right now we just have the halogens. So at the same time that this lone pair of electrons is coming in and forming a bond, this bond is breaking to the leaving group. Okay. And then we form, in this case, methanol and bromide, okay. 2 lone pairs of electrons that are missing on there. Don't let that throw you off. That's just a typo from the slide. Okay. So this is another example of a concerted reaction. Okay. Everything happens at once, meaning that there's a big transition state, right? But there's no intermediate to isolate here. Everything's happening at once. Okay. And notice what's labeled down here at the bottom, backside attack. The nucleophile is attacking the backside of the carbon that contains the leaving group. And that's because the leaving group blocks approach from any direction. Okay, there's electron density here in the electronegative leaving group, and that's going to block the approach of the nucleophile from that way. Okay, so it comes in from the other side. It's also supported by molecular orbital theory, right? The HOMO the non-bonding sigma pair must overlap in phase with the LUMO, which is the anti-bonding sigma star, for the electron transfer to happen. Okay. So that supports, right, molecular orbital theory supports backside attack. Notice it can't happen here with frontside attack because they're not in phase. But the easiest way to think, right, jumping back a slide here, bromide's blocking the approach from one way, your nucleophile has to come in from the other direction. Okay. Why is it bimolecular? Why is it SN2? Well, we've already mentioned this, right? Both the nucleophile and your original alkyl halide are involved in the transition state. Right? This is what your transition state looks like. Delta negative on your hydroxides, this bond is forming. Delta negative on your bromides, this bond is breaking. Those are happening simultaneously. So both the nucleophile and the alkyl halide are involved in the transition state. Changing the concentration of either changes the rate of the reaction. So that's why this is bimolecular. Substitution reaction starts with the nucleophile, bimolecular, SN2. So the big takeaway right now, understand all those factors that affect the reaction and know the reaction mechanism here from slide 14. In our next video, we'll see factors that can affect these substitution reactions. And then after that, we'll talk about SN1 mechanisms. Okay. And in the back half of the chapter, we learn about those elimination reactions.